Hello, everybody. My name is Jesse Rodriguez. You may be watching this video, one, because you're a student in my ME 461 or 561 class, uh, or you might just be a person who stumbled upon it. The point of this video primarily is actually so that I can flip the class in whatever way I want, and send students to lecture materials, asynchronous lecture materials whenever they need them. The truth is that this material is not very refined yet. Uh, Better quality versions of these lectures are forthcoming, and I plan on producing them. But for the time being, I figured I might as well get some lectures up online so that people can access them uh, as easily as they may want to. Okay, so let's get started. So, what is this class? What is this? What is the topic that we're covering here? Well, the class is called gas dynamics, which is actually a term of art that's used to describe the branch of fluid dynamics or fluid mechanics where the flow exhibits significant changes in density. This is what you normally would call compressible flow, which is more common term or name for the course. It's the name that I would prefer. So let's talk about compressible flow a little bit. There are some important regimes and applications. So important compressible flow regimes and applications. So importantly, compressible flow effects become important when the Mach number, which is a parameter that you'll become very familiar with in this class, is greater than about 0.3. Important when the Mach number, which is defined in the following way, where we typically write it as capital M, and it's defined, the three horizontal lines denote a definition, is defined as U over A, where U is the mean flow velocity, and A is the sound speed velocity. In the medium in question. When the Mach number M is greater than or equal to 0.3. And I made the bottom sign of that greater than, or sorry, that bottom line in the greater than or equal to sign squiggly because it's a fuzzy line. It's not a hard line. Like most things, when you get to advanced topics like compressible flow, you're going to encounter fewer and fewer hard designations and easy bright lines to draw in the sand to separate different flow phenomena. I do believe that the first homework assignment includes a justification of this cutoff. So we'll leave that a justification of that value to the homework. But just know that when the Mach number starts to climb above 0.3, things get a little bit squirrely, and it doesn't look like normal fluid mechanics anymore. The density of the fluid can change quite a bit. So in general, the types of things that I want you to keep in mind, I want you to think about transonic, meaning Mach number of about 1, That's m approximately 1. Supersonic, which would be, of course, m greater than 1. Aircraft, so aircraft moving at those speeds. We also will think of propulsion systems. Even if the overall aircraft is not moving at speeds approaching a Mach number of 0.1, the flow within the propulsion system or engine might be in a compressible flow regime. So you need this analysis to be able to design those types of systems. And other extreme scenarios that's not how you spell scenarios. Scenarios like re-entry. So now we're talking about a capsule, say, re-entering the atmosphere from orbit. So in general, we're sort of talking about things like jets and rockets. Okay, those are the devices that we've come up with that utilize this, that play in this regime of physics. Okay. What you'll often hear is that at the 1,000 foot level, compressible flow is a collision between fluid mechanics and thermodynamics. Okay. So many of you may have had a fluid mechanics course before. At least I hope you would have. You've definitely taken some thermodynamics. However, just taking a thermodynamics course does not necessarily mean that you're comfortable with the topic, as I'm well aware. So we will spend some time reviewing these concepts today in today's lecture. Okay, so before we do that, though, before we go into a review of basic thermodynamics, let's get some units issues out of the way. Okay, so in this class, you may be asked to, I mean, I'll try to keep it to a minimum, of course, but you may be asked to translate between imperial units and metric units, and so it's worth taking a moment to kind of clarify the different types of units and measurement systems that are used that we may encounter. So the first thing that I wanted to bring your attention to was the pound force, often just abbreviated LBF. So the way this is defined is that 1 pound force gives 1 slug of mass and acceleration of 1 foot per second squared. Okay, 1 slug is equivalent to 32.174 pound mass. Okay, so this is a little different than SI. So by analogy, 1 Newton gives a 1 kilogram mass, an acceleration of 1 meter per second squared. Okay, so it's a little bit cleaner in that way. If you actually work with these values, it becomes clear why they made this choice of defining the slug in that way. But it has to do with the acceleration due to gravity on at ground level. However, it is a little confusing that you have, in essence, one pound force interacts with 1 pound mass in a different way. It's like you want it to be 1 Newton accelerates one kilogram to 1 meters per second squared, but it's 1 pound force accelerates 32 pound mass to an acceleration of 1 foot per second squared. So it's a bit messy in that way. But and that kind of conversion can be very confusing, which is why we bring it up here. So another thing that you may not have seen before is the specific volume. I will denote this with a lowercase v with a little tail on it, not to be confused with a nu. Okay, so this is defined as the volume per unit mass. Okay, so what it is it's just mass density inverted. So we just say that this v is 1 over rho. Okay. So nothing too exotic going on there, but it fits within this overall motif of mass specific quantities that we'll often be working in terms of in this course. You also have this note on pressure. This is often brought up in an introductory thermodynamics class. The difference between absolute, ambient, and gauge pressure. In general, in this class, we're going to be using absolute pressure, which you can define as the ambient pressure plus P gauge. So this absolute pressure, P abs, is the pressure measured relative to perfect vacuum. I always put 2 C's instead of 2 U's for vacuum. Okay, so the gauge pressure is the pressure pressure measured relative to the ambient, of course. Rel to ambient. But for our purposes, we're just going to use P abs. Okay, that's what we'll be focused on in the course. There's also this concept of viscosity. Usually denoted with the lowercase Greek letter mu. This thing is defined as the shear stress divided by the rate of angular deformation. At least in words. It'll come into some of our discussions, but it actually won't be overwhelmingly important for us, so not too important. There's also another quantity which is called the kinematic viscosity. So that's mu over rho, and that is the Greek letter nu. Okay. Just another common measure of viscosity that you might see. Again, not super important for this course. And then another thing that I wanted to discuss is the gas constant. So we'll spend a lot of time talking about the gas ideal perfect gas equation of state. Something that we'll use a lot. Things depending on what kind of scenario you're in, you'll have different assumptions. So like when you're in traditional fluid mechanics and dealing with high density liquids, you actually just assume that the density is constant, right? Assume rho is some constant. But in our case, i.e. for gases, we will typically use the ideal gas equation of state, which, you know, everybody at this point should be familiar with. I'll write it in its mass-specific form here, where it's P equals rho RT, okay? But this is where I wanted to make the case, or make the point, that there's actually a lot of different versions of this gas constant R, okay? So the gas constant R here is actually, you can write it this way, where you have R hat. Now R hat is the universal gas constant, okay, divided by the molecular weight of the of the gas, and it's the average molecular weight, okay? So average molecular weight. So that's why you can have an effective gas constant for air, for example. This R hat is the universal gas constant. The units of R, which I'll write in square brackets here, are joules per kilogram Kelvin. Okay. And like I said, you can have, we'll typically be dealing with air, and R for air is approximately 287 joules per kilogram Kelvin. Now, I said that the R hat is universal. Well, R hat itself is a combination of two fundamental constants, which is the Boltzmann constant times Avogadro's number. Okay. Now, the Boltzmann constant is the most fundamental version of the gas constant, you could say. It's the one that's preferred by physicists. Its value is 1.38 times 10. 1.38 times 10 to the negative 23. And this one is just joules per Kelvin. We're no longer working on a mass basis here. The units of the universal gas constant are joules per mole Kelvin. Being multiplied by the number of molecules per mole. Okay. And yeah, so let's sort of rewrite the gas constant here. So, or sorry, the ideal gas law. So if we use the universal gas constant, then we could write PV, and you'll notice that I wrote the V in a little bit of a strange way there, equals N hat R hat T. I'm writing N hat here to denote number of moles of the gas, and this V with a hash mark in it is just volume. Okay, because in this class we'll be dealing with cases where we have a flow velocity V. You could use a U as a flow velocity. That's often used in fluid mechanics, but the problem in this class is that U is the most often used symbol for internal energy. So V kind of gets overloaded. For that reason, when I write specific volume, it'll always be that lowercase V with the tail, and then for plain old volume, it's going to be a capital V with a hash mark, just so that it doesn't get confused with the capital V that is talking specifically about flow velocity. Okay, so that's what we're doing there. So that's one version of the ideal gas law. You can also write it in terms of the Boltzmann constant, where you have P V equals N, where now this is literal number of particles times kBT, or P is equal to lowercase n kBT. Again, these are the forms preferred by physicists. N is just what would be called the number density, or the number of particles per unit volume, that's where you get the capital N divided by capital V. Okay, so just wanted to make that point. You know, having these different constants floating around can often be confusing. So those are the fundamental differences between the different gas constants that you have available to you. Okay, so let's go over some basic thermo. Let's take it back. So let's really ground ourselves here and go back to the true basics of basic concepts of thermodynamics, and talk about the definition of properties. So properties are characteristics that describe a state. Oops. We have intensive properties. These are properties that are independent of mass. So in this case, you have something like temperature or pressure or specific volume, right? Because you've normed the mass out of that. And then you also have extensive properties. And you might guess that this is dependent on mass. So examples of this are things like the actual scalar volume, the internal energy U of the system, the entropy of the system, capital S. Okay, there's also a separate dichotomy within properties, is you can also define, or not even dichotomy, it's a trichotomy. You can define these properties as observable. So these are things that you can measure, like the temperature, the pressure, and the total mass in a system. So mass M. Okay. There's also defined properties. These are things like density. You measure the volume and the total mass, you get the density. The enthalpy is a defined quantity. And also things like the specific heat capacities. We'll talk about those in a bit. And then there's also quantities that are derived. So things like the internal energy of a system or the entropy. And the way you get these things is from thermodynamics. Derived via Thermo. Okay, using some physical intuition, starting with the fundamental laws and proceeding from there. Okay. There's also this notion of a thermodynamic process. So this is the path from one state to another. Okay, and so if it is a adiabatic path, here, let me get rid of this star symbol there. Adiabatic is defined as a process where there's no heat transfer occurring. So the way I would denote this is with this curly d delta, lowercase delta q, is equal to 0. Okay. There's also isothermal. The big hint is in the name with this one. This one's defined as the case where there is no change in temperature, dT is equal to 0. There's also isobaric. Again, hint in the name, bar being a unit of pressure, dP equals 0, isobaric. We also have isentropic, where the entropy is equal to 0. And then we also have one that's often not discussed is isochoric, which is defined as the system volume not changing, so a constant volume process, dV equals 0. That's what comes here. Okay, and then a cycle is defined as a set of proper processes that return to the same state. Okay, some very, very fundamental stuff that hopefully you've seen before. So let's go ahead and jump right in and talk about the laws of thermodynamics. Okay, and the textbook for this course is a textbook called Gas Dynamics by Zucker and Vibelaars, and they actually include two zeroth laws, let's say, of thermodynamics. One of which I hadn't seen before, but is actually, I think, definitely worthwhile to make note of, which they call the 0 squared law. So sort of like the 0th law before the 0th law. And there's this thing that we do in thermodynamics where we assume the existence of a relation among the system properties or an equation of state. So we assume the existence of a relation among the system properties which we term an equation of state. So this thing might be, extremely complicated. It might even be undefined. But we assume it exists. Okay, so like when I say it might be undefined, is it might be given by a table, but we're assuming that this fundamental relationship between these properties exists, which allows us to kind of close our analysis of these thermodynamic systems. So for a simple compressible system, which is something that where you have no electricity and magnetism, no E and M, major gravitational potential gradients, no kinematic or surface tension effects. Essentially, this is like an ensemble of particles in a sealed box. Okay, just particles bouncing around. Only two independent variables for independent intensive properties. It's important that they're intensive. So only two independent intensive properties are required to fix the state. Are required to fix the state. Now, you actually may have heard this before. I remember the first time I heard this, it was almost given as a maxim, where they say they didn't add all these caveats about it being a simple compressible system. They just said all you need to fix the system is two independent intensive properties. Um, but the reason why has to do with the fact that in that case, in that simple compressible system, if you proceed from fundamental statistical mechanics, your equation of state ends up being just the ideal gas law. So the question is, why is this the case? Well, our equation of state, I'll denote that EOS, is P equals N kBT. And that's an equation relating three properties. If you specify N and T, you get the pressure. The other thing that's important is that you choose properties that can be varied while holding the other constant. But that's sort of a bit of a pedantic point. But our equation of state is P equals N kBT. So if you fix N and T, you get P, and your equation of state is sort of defined, and your system is set. Okay, so there's no more room for variation in your equation of state. That's why those two independent intensive properties fix a simple compressible system. Okay, so that's a little bit of a digression about the zero squared law, but still an important assumption that we make. The zeroth law, let's go ahead and underline these guys. The zeroth law, this is more commonly noted or brought up in thermodynamics textbooks, but it's like extremely obvious. It's seemingly the idea is that we have this transitive property of equilibrium. So what I mean by that is, let's say that we have these three systems in contact with one another. System A, System B, and System C. And then these walls here that we have between the systems are non-adiabatic. So in other words, they allow heat to transfer between the systems. So if essentially what this says is that if A is in equilibrium with B, and B is in equilibrium with C, then A is in equilibrium with C. Okay, so if the temperature of A and B are the same, or and the temperature of B and C are the same, and the temperature of A and C are the same, seems extremely, temperature of A is equal to temperature of C. Seems like it's sort of true on its face, but it still forms a fundamental law of thermodynamics, sort of an axiom that we need to keep, that needs to be true. Okay, so then let's proceed to where we're really starting to actually encounter some physics here, which is the first law of thermodynamics, often referred to as just energy conservation. So what this means is that for a closed system, if you sum over all the heat the heat transfer in process I, that's going to be equal to the work done by the system during process I. So this subscript is referring to process I. Okay. Real quickly, we'll talk about sort of our sign convention here because this can often trip people up. Work transferred from the system is positive, and heat transferred to the system is positive. Okay. So if you're ever kind of confused, come back to those two sentences to convince yourself that you have the signs right. What you might write this for a single process is that the delta E is equal to Q minus W. Okay. So what is this capital E here? So capital E is total energy. On a per mass basis, you could write it as lowercase e is equal to lowercase u plus v squared. Now that's that flow velocity I was talking about. This is a kinetic velocity plus g times z. So you're getting your kinetic and potential energy in there on a per mass basis. This is meant to be a lowercase u here. So this is total energy per mass. And then the capital E is just total energy. So for a system at rest, you have velocity equal 0, and also, gravitational potential energy differences are not important. So you typically just lift the internal energy out, and you can write this in quote unquote differential form as du is equal to delta q minus delta w. Okay, notice the transition to lowercase letters there. Okay, so then let's talk about what we're seeing here. So I mentioned this before when I wrote down the adiabatic process definition, but there's this delta here, right? And that denotes that this is what's called it's not an exact differential, because W and Q are what is known as path functions. Okay, what's a path function? A path function is not, so, the work and the heat don't have a value at a certain state, right? You have to move from one state to another for work and heat to be transferred or to occur. So that's why they're called path functions. They're not actually state variables, whereas the internal energy has a value at a certain fixed state, and so therefore it's a state variable. Now, for a moment, I want to talk a little bit about total differentials. What here is just like a lowercase d, okay? And this is kind of a, we'll call it a mathematical aside. Focusing on total differentials. So this is a mathematical object, let's say, that only really is used in thermodynamics, and particularly like classical thermodynamics. There's a rigorous version of it called differential forms in mathematics, but there's a bunch of additional formalism to go along with those, and they're often also in mathematics. Those are used for like differential geometry, not so much for the types of analyses that you carry out in thermodynamics. So because of that, many people have not seen total differentials before. And so I wanted to take a moment to describe what was going on here so that nobody gets confused when we look at some of these later investigations where we'll be using these total differentials. Okay, so the way you define it is the following way, where you say a total differential is the infinitesimal change in a function at a point. In a function at a point, it involves some abuses of mathematical notation, but it's very useful, especially in the context of thermodynamics. So let's suppose that we have some function f, which itself is a function of x and y. It's a function of both x and y, okay? The total differential of f, capital F, is df equal to the partial derivative of the function that f of f, so like that lowercase f, the partial derivative of f with respect to x, holding y constant. That's what this notation means. So the parentheses with the subscript are telling you precisely what's being held constant when you take that partial derivative, and then you multiply that by dx, okay, the total differential of x, plus the partial derivative of f with respect to y, holding x constant, dy. Okay, so this notation of partial derivative you probably only would have seen if you were in upper division physics class, but that's all it means. It's just a partial derivative, but you're just specifying which variables are being held constant when you take that partial derivative. Okay, and so essentially what this is saying is just that if you move from a point xy to x, if you move from the point xy to x plus dx, say, and y plus dy, the resultant change in f is df. Okay, it's an infinitesimal change. So how do we use these? Okay, well, the most important thing is that we can integrate. You can integrate these to calculate total changes during a process. Total changes during a process. You can substitute, okay, so you can substitute some total differentials into other expressions to build more complicated expressions. Also to one, and this is a common technique um, in in the physics analysis of thermodynamic systems. There are these relations called Maxwell relations that have to do with substituting in total differentials, looking at equality of mixed partial derivatives in order to relate different thermodynamic quantities to one another. So you can do algebra with these. So like let's say that x itself is a function of z. Okay, so then the total derivative of, or total differential of x is actually equal to dg dz, and I don't have to do parentheses around it because g is not a function of any other variable. So you can then substitute that into the expression we had before. So df is equal to df dx holding y constant times dg dz dz plus df dy holding x constant dy. Okay, so I just took the dx that I got here and substituted it into its place. Okay. The one thing that you really need to keep in mind is that you must refrain from dividing total differentials to form total derivatives. So refrain from dividing total differentials to form total derivatives. So, like for example, df dx is would from this analysis would end up being df dx holding y constant plus df dy holding x constant times dy dx. This thing is not defined and leads to issues. The only case where this works is when you have a function of a single variable, and that's just because the definitions are comparable. So this works with function of single variable, and that's just because the literal definition of the total differential is like df is equal to f prime of x dx. So an x there. And the derivative of f with respect to x is defined as f prime of x. So you can move that dx over in this case where you have a function of a single variable f of x, but that's just because when you write down the definitions, it works out that way. It's not that the total differential objects are meant to be divided by one another in this way. So whenever you have any system with multiple variables going on, just do not refrain from dividing total differentials. It'll cause you some issues and give you some mathematical nonsense. Okay, so that's our aside on total differentials. I just wanted to spend some time going over that because people may not have seen this topic before, this structure before. Hopefully it'll help as we start writing these up in our notes. So okay, so let's go back to the first law. We had this internal energy equation here, which was du, so the total differential of the mass specific internal energy was equal to delta Q minus delta W. let's deal with some of these path functions here. In general, we would like to be able to express our system fully in terms of state variables, because then we get this. We can describe our system at a certain point, at a given point, right? So let's work with the work term first. So in general, how do we define work in terms of a force? Well, the way we do that is it's an integral, right? The total work done is equal to the integral of F, whatever the force it's acting on the system, dot dx. Okay, we'll assume that this is a 1D system, so it's not a vector product here, vector dot product. But this whole thing together is actually delta W. Okay, so we're integrating delta W to get F. Well, in a simple compressible system, the force in this case is just going to be pressure acting over an area, right? Because that's we're talking about essentially gases running into a wall, causing some sort of expansion in a cylinder, say. That's the work being done. And moreover, we could look at the A times dx, so that wall moving a little bit, some incremental distance dx, and this thing we could rewrite as dv, the infinitesimal change in volume. Okay, and so by using these two relationships together, we can see that our delta W, we can actually rewrite that as P dV. Right? And again, moving back to the per mass basis. Because we're looking at F dot dx, the F is P times A, and A times dx is just dV. And so now we've replaced the delta W for the case of a simple compressible system with PdV, which is nice. Okay, so now that leads us to du equals delta Q minus PdV. We'll deal with the delta Q in a bit once we get to the second law. But now is actually a good time to define the enthalpy. So the enthalpy is defined in the following way, where we take U plus PV. Okay? So if we take the total differential of that, we get dH is equal to du plus P dV plus V dP. That's just chain rule. Okay? So if you take the total differential of PV, you get dPV, or yeah, dPV plus VdV. And using these two relationships together, we can sub in what we had for du and see that dH is also equivalent to delta Q plus V dP. Okay, and again, enthalpy is a defined quantity. It's useful in our analyses. You'll see in detail why it's useful later. But in essence, it's really it really has to do with this interplay between internal energy and pressure and volume in a simple compressible system. That's why we define it that way. Okay, let's also while we're at it, define the specific heats. So the specific heats are the specific heat at constant pressure, and that is, or Cp, is defined as the partial derivative of the enthalpy with respect to temperature at constant pressure, okay? And then we also have Cv, which is defined as the partial derivative of the internal energy with respect to temperature at constant volume, okay? And again, these are things that will pop up as we start to delve into these systems, try to solve some problems. Okay, so that kind of concludes our discussion of the first law, going over some of, going over some of the fundamental equations surrounding that thermodynamic law. Now let's go into a discussion of the second law. Now this is where things get interesting and confusing for most people. Okay, so this is for me where it becomes difficult to teach thermodynamics without really going into the gory details of statistical thermodynamics, because in an undergraduate course you're typically limited to teaching people about the concept of entropy, which is what the second law is all about, by going about it the historical way, which is a little bit confusing, because this is back when our physical understanding of what was happening on a micro scale with these larger processes was completely incomplete. Was entirely incomplete. Okay, and so let's I'll write it this way. So the historical way of stating this law is that essentially, so let's write it this way. Let's say the historical way is to say that not all heat from a cycle can be converted into work. Okay, or another historical way of saying this is that heat always flows from, or actually there's a key word here, flows spontaneously from hot matter to cold matter. Okay, so this is the work of Rudolf Clausius, in 1854 rather. Okay, so those two statements actually give rise to the concept of entropy. And so, if you just look at the first law in isolation, it's perfectly happy with heat flowing from cold things to hot objects, right? But the second law tells us that this doesn't happen. And this is where this sort of concept of the arrow of time comes from. You may have heard that somewhere along the way that the second law provides us with an arrow of time, and that's what they're referring to, is that it sort of gives us a basis for stating a preferred direction for things to proceed. Okay, so here's kind of the story of how we got here. Okay, so we have a a statement from Carnot. Now, some of you may remember from your thermodynamics course the Carnot efficiency. So Carnot in 1824 said that, you know, there is a maximum efficiency for an engine operating between two temperatures. And it only depends on those temperatures. So it would be eta C is known as the Carnot efficiency, is equal to 1 minus Tc over Th. Okay, so I'm sure that many of you remember seeing this. Okay, so Clausius was picking up this. He was trying to work out a real mechanical theory of heat. Okay, in the late in the 1850s and 1860s, and in 1962 is when he develops the concept of entropy, or 1862, I should say. Sorry. So what he's trying to do is he wants to quantify the amount of irreversibility by defining something that is path independent, meaning another state variable. So these path quantities say you can move along a certain point in a state diagram and return to the same point, and you'll have some net heat that's occurred, right? Your heat or net work done. But if you return to the same point in the state diagram, if you return to the same pressure and temperature as before, your density better be the same as before, right? Because you're plugging into the ideal gas law, you should get the same density out. And so state variable is known as path independent, meaning you could go in every direction you want. When you return to the same point, you should have the same value of that state variable that you had before. And so Clausius was looking at these processes, and he was seeing that there were some losses due to heat, and there was also this thing that was associated with the transformation of heat into work that made it so that all of that heat couldn't be perfectly converted into work, and it was kind of like this amount of irreversible loss, and he wanted to find a way to quantify that cleanly. Okay, so let's see. What he said in 1862 was, I want to quantify irreversibility by defining a new path independent state variable. And you know, spoiler, this would end up becoming the entropy, right? But really, he just wants to find a consistent way of accounting for the conversion of heat to work in this path independent way. So remember, we had at this point, even in 1862, we have this idea, this du is equal to delta q minus delta w. So we replace the delta w with pdv. Happily, those are two state variables. We're happy to use those. But this thing, this delta q, is gross. Right? It's a path function. It's not expressed in terms of state variables in the way that we would like. Okay, so then what Clausius did is he said, let me isolate delta q. Okay, and he's going to write it as du plus p dv. And then he said, let's assume that the internal energy is a function of the temperature and the specific volume, which is perfectly legal. Like we said, if you set two independent variables, intensive variables, then that sets your whole system. So you can assume that any state variable that you know of is some function of another two state variables. So for his analysis, he just said that that internal energy is a function of v and t, and that allowed him to expand the total differential of u in the following way, where he has du dt at constant v times dt plus du dv at constant t dv plus p dv. Okay, and we already know what du dt at constant v is, right? That's the specific heat, cv dt, and then you're left with this quantity du dv at constant t plus the pressure times dev. Okay, so let's see so this is what delta Q is equal to. Now, if delta Q was itself, let's see. So he's like, let's assume that Q is some sort of like is a path function, right? Then we would have an actual total differential of Q. This is what we want. What we want is something like dq. We want q to be a state variable, and if it's a function of v and t, you would end up with dq dt at constant v dt plus dq dv at constant t dv. Okay, so that would be like if we calculated the total differential of Q as if it was a proper state variable. Now, if it's a proper state variable, okay, meaning it's integrable, then we expect that we get this equality of mixed partials. So we expect that if we take the partial derivative with respect to v of this first term dq dt, so we expect dq dt dv to be equal to d squared q d v dt. In other words, if we take the partial derivative of this guy with respect to v and the partial derivative of this guy with respect to t, we would expect those things to be equal because we have equality of mixed partial derivatives, and this is a proper total differential, integrable total differential. Okay, but this is not the case. So let's say that if we do this, test it with our actual delta Q that we have, what we end up with is that dCV dV at constant t. This thing goes to 0 because CV is not a function of V. And then d by dt of du dv. This du dv itself already goes to 0 because we know that u is a function of just t for an ideal gas system. And then you have P here, right? And d by dt of the pressure is not equal to 0. So here we have basically this doesn't work out. So not equal, right? So in order to make this work, what we have to do is introduce an integrating factor to make delta Q behave like a state variable. Introduce integrating factor. Now, the integrating factor in principle could be a function of both temperature and volume, but this is where Clausius looked back at Carnot's work and said, look, his fundamental efficiency depends only on the temperature. So therefore, I'm going to say that my integrating factor F of T is a function of just the temperature due to Carnot. Okay, just temp due to Carnot. Okay, now this is where it's interesting to make a digression, because this is part of a correct derivation of the sort of differential definition of the entropy, or a way to define the entropy. However, it uses Carnot's efficiency, which Carnot himself was derived in an incorrect way. So let's actually look over here at or never mind, I'll look in a moment. But when Carnot came up with his efficiency, he was thinking of things like water wheels. Like he was saying that the maximum amount of energy that you can get out of a water wheel is the difference in potential energy from the top to the bottom of the water wheel, right? And so he was thinking, okay, I have some sort of temperature at the top and temperature at the bottom. That's like my potential energy, and the maximum amount of energy that I can get out of those divided by the total amount of energy in the reservoir is going to be the my thermal efficiency. And he's using this concept of caloric, the flow of caloric, to come up with this, and turns out that's incorrect. But even though his reasoning was incorrect, he came up with a correct maximum efficiency between the two reservoirs. So kind of interesting. So he's getting there through incorrect reasoning, getting the right answer, and then Clausius 40 years later is using his work and citing him for his choice of integrating factor here. Things are just kind of falling in place, but again, they're all confused. The physics basis, the first principles are actually wrong, and that's why understanding this stuff, going through this route, this historical thermodynamics route, isn't maybe not the best way of trying to understand these concepts. But regardless, we proceed to try to develop this concept of entropy by solving for the integrating factor. So again, remember, just to recapitulate here, Clausius saw that we can't convert all the heat that we give into a system into work, and he's like, okay, I want to quantify this irreversibility by developing a new path-independent state variable. And he started by just solving the first law for the heat transfer, and now he's going to start working with that differential identity to get something path-independent out. And so what he does is he takes this F, the integrating factor, and you multiply both sides of that identity that we had before, which was delta Q equal to CVT plus that quantity times dV. And so it's F times CV dt plus the quantity F times du dV, holding T constant, plus that quantity F times P dV. Okay, so now this is he multiplied the integrating factor, and now let's do that procedure again, where we take the partial derivatives with respect to the other V and T to check for equality of mixed partials. But now we've introduced this integrating factor to allow us the leeway to make this into an integrable total differential. Okay, so let's go ahead and do that. So if we do d by dv of F times CV, holding T constant. So again, F is just a function of T, right? And CV itself does not depend on the volume. So we know the whole left side still goes to 0. And this is what's nice about being able to say that F is a function of T only. Again, based on Carnot's efficiency. And so the left-hand side of the equation goes to 0. But then we have d by dt of this quantity F du dv t. And again, I told you before that du dv itself actually goes to 0. This is because u at this point was known to only be a function of temperature. To be precise, for a monatomic gas, you can write it as, let's say that we're talking uppercase U here. You can write it as 3/2 nkBT. Okay, n being the total number of particles. We can also write it on a mass specific basis, lowercase u, 3/2 RT. Okay, that's some of that interplay between the different gas constants that you can have. So there's no v dependence there. So when you take the derivative with respect to v, it actually just drops out. And then we have F and P here times dV. Okay, and so let's go ahead and do the product rule here. So we have 0 is equal to F prime of T times P plus F of T times dP dt, which we know is just, we'll use the physicist formalism here. We'll do NKB over V. Okay. And the pressure itself is NKBT over V, right? So then we can divide both sides by NKB over V. And what you end up with is F prime of T times T plus F of T, which is just an ODE, okay? A first order ODE. And so you can check this yourself, but it turns out that the solution to this first order ODE is actually just 1 over T. Okay, the general solution. Assuming a boundary condition that allows us to put 1 there. That's kind of a free choice. And so what this means is that delta Q over T, so that's F times delta Q. Delta Q over T is itself an exact differential, because it has that equality of mixed partials that will make the integral a path independent. So if you do an integral and return to the same spot along your integral, you'll get 0, right? You'll return to the same point. And so that is an exact differential. The integral of delta Q over T is path independent. And we define ds as delta Q over T, with S being the entropy. Okay, so this is exactly how, in fact, Clausius came up with the concept and defined entropy when he published his memoirs. Okay, so then he proceeded after coming up with this definition. And again, it's like, I don't know how useful this is. I mean, the last several minutes here might have just been like complete. Might have seemed like a really wide, useless digression, but I do think it's worthwhile to see where the concept of entropy is coming from, starting from the first law, and how Clausius came up with the idea. And it's almost an exercise in showing you that this is the best I can do to teach you where entropy comes from without going to the statistical mechanics, which is where you actually learn and have a really good understanding of what's going on with entropy. You might have heard some nebulous idea that entropy is a measure of disorder, but you've never seen that. You've never really mechanistically understood that in your thermodynamics coursework. And so, you know, unfortunately, we know how to do simple calculus here. So I've shown you some total differentials. So we work with those to develop the idea in the same way Clausius did. And hopefully, this being an upper level course, it's useful to see how he came up with this idea in the first place. Trying to reconcile, work the heat transfer into a path independent quantity. However, that's where this leaves us. Okay, so once he defined the entropy, he showed, and this is another statement of the second law, actually. Showed, and this is also known as the Clausius inequality, that on a closed integral, that's what that little circle means. So a path integral where you return to the same point of ds for all processes is less than or equal to 0. Okay, with the path integral, the closed loop integral of ds being equal, so with equality, for reversible processes. So after he came up with this definition for entropy for ds, he then proceeded to show that this was the case, and that as a result, direct results or a corollary of the second law as stated before. Okay, so what this means, so this may seem a little strange because you're like saying that the entropy is actually less than 0, but what's happening here is that you have excess entropy is produced in the surroundings for an irreversible process. And that just has to do with that sign of the heat transfer, sign of delta Q, right? This is why you may have heard this, that ds of the universe is increasing. And this is super interesting. So this is where we'll scroll up and look at some pictures here. So these are portraits of Clausius and Carnot. I think that portrait of Clausius was actually taken pretty close to his death, and Carnot's portrait here was taken very young when he was like 17 years old or something in the French military. So that gives you an idea of the two folks who came up with this idea. And if you go, you can actually go and find Clausius's memoirs on the mechanical theory of heat online. It's easily available. And I actually encourage you to read them because they're stunningly modern and easy to read. In fact, Max Planck once said that it was reading Clausius's memoirs that made him stick with physics, because all of the other people that he was trying to learn from were completely unintelligible, and Clausius's writing was so clean and understandable that it encouraged him to continue on. And you know, Max Planck has a it's hard to overstate the importance that he's had. In fact, that constant, Boltzmann's constant, was actually is actually due to Max Planck. It's sort of mistakenly named after Boltzmann. Yeah, so it's quite kind of interesting there. But I do want to bring note to this is that he ends his 8th memoir on the subject with this just like stunningly modern statement where he says, "We may express in the following manner the fundamental laws of the universe, which correspond to the two fundamental theorems of the mechanical theory of heat. 1, the energy of the universe is constant. 2, the entropy of the universe tends to a maximum." And he wrote this in the 1860s. And so it was that a man foresaw the heat death of the universe, and stated such in plain language. And so I just think that's quite remarkable. Yeah, so that is how we end up with this idea that the entropy of the universe increases from Clausius's reasoning. And so let's assume so remember that the process has to be reversible for delta Q over T to behave like a path independent quantity. So if we assume a given process is reversible, then we can replace delta Q in that du equation with T times ds. Then we can write du is equal to T ds minus P dV. And I'm going to box this because it's quite important. In fact, I'm going to frame it like Dr. Lazzati over in the physics department used to draw frames around equations when they were particularly important. So this is a very important relation. This is sort of let's say a combination of the first and second law. It's true for simple compressible systems. However, and it's important. So it's a key starting point in the analysis of thermodynamic systems. But even though we assumed that the process was reversible to derive this relation, it contains only quantities that are path independent, and because of that, it's valid for all processes. Okay, so we assumed the process was reversible so that we could replace delta Q with TdS, but the resulting equation that we got contains only path independent quantities. So contains only path independent quantities, and therefore it is valid for all processes. That 3 dots are signified therefore. Valid for all processes. Okay? So that's why it's such a useful, important equation. You can always use it. Okay, and that concludes our discussion of the laws of thermodynamics. Let's see. We'll have a little bit more to cover here, and then we'll be done. All right, maybe 10 more minutes or so. Okay, so let's talk really quickly about a couple more details in this review of thermodynamics, and then just to clear this up, and then in subsequent lectures we'll actually get into the meat of compressible flow. So perfect gases. Okay, so let's define this. So a perfect gas is something that obeys the ideal gas law and has a constant specific heat. Okay, so what does that mean? That means that we are ignoring intermolecular interactions. And that means, I truly mean that the ideal gas law literally assumes that you have point particles that are not colliding with each other. They're infinitesimally small, and they just go until they hit a wall, and then they bounce off speculatively. That's what the ideal gas law assumes. Okay, so you're ignoring intermolecular interactions. And any internal energy structure. What do I mean by that? Well, there's of course the atomic structure associated with with the atoms, but what I also mean is things like vibrations and rotations. So, you know, our atmosphere is primarily nitrogen, which is a diatomic molecule. There are like two nitrogen atoms on a line, and this thing can rotate this way, it can rotate this way, and so those two rotational modes are pathways for energy, and so the ideal gas law and all these things ignore those things. So the following results can actually be derived from statistical thermodynamics, but I'll just go ahead and state them here, and we've already alluded to these. So we know that the internal energy for, and this is for a monatomic ideal gas, is 3/2 NkBT. And again, before I even showed this, we had it as U is equal to 3/2 RT on this per mass basis. Because so if you look at the enthalpy, for example, and you have U plus PV, PV itself is just equal to RT, right? The ideal gas law. So H is equal to 5/2 RT. Okay, and so what this means is that that CV, which is equal to du dt at constant volume, is equal to 3/2 R, and Cp is equal to partial derivative of the enthalpy with respect to temperature at constant pressure. It'll just be 5/2 R in this case. Okay. Now there's a value, another very important value that you'll encounter a lot, which is gamma, or the ratio of specific heats. It just so happens that these specific heats are often found when you're looking at, say, the entropy change between two states or something, in a ratio like this, Cp over Cv. And so for a monatomic ideal gas, it looks like this. So this is monatomic perfect gas. Okay, I'm going to box this because this is quite important. For a diatomic gas, like air is approximately diatomic, gamma is equal to 7/5. Okay, so this is the value that you're actually more likely to be using, 1.4, when you do your analysis in this course. Okay, and that has to do with the excitation of those additional energy pathways. You know, the air gets those additional two rotational modes excited, and so you get another factor of 1/2 NkBT for every independent mode. There's a theorem in thermodynamics called the equipartition of energy theorem that gives rise to that change in gamma. Okay, let's also quickly write the formula for entropy change. Let's get this zoomed right here. So for entropy change, we have delta S from state 1 to 2 is the integral from 1 to 2 ds, which we can rewrite using that sort of fundamental thermodynamic quantity relation as 1/t du plus the integral from 1 to 2 of p/t dv. We can rewrite du as cv dt. So the integral from 1 to 2 of cv over t dt plus, using the ideal gas law, r over v dv from 1 to 2. And so what you get is cv natural log of t2 over t1 plus r natural log of v2 over v1. and there's a lot of ways that you can actually recast this using the ideal gas law and other equations. Okay, but that's one way that you can express the entropy change. Okay, and then the last thing that I wanted to sketch out for you here that you've probably seen before is this idea of the polytropic process. And then we'll be all done. So let's look here. The polytropic process is the following, where you have P times V to some integer, or not even integer, to some value, N, is equal to is equal to a constant. Okay, so the way that that looks here, if we're going to write out PV and TS diagrams, which are very important diagrams for understanding thermodynamic processes that you'll draw many times in this course. So we have 4 lines to draw here, 4 sort of key polytropic processes that I'd like to bring your attention to. So N equal to infinity is this vertical line. N equal to 0 is the horizontal line. That would be P equals constant if you just look at that PV to the end. You have N equals 1. So this is a 1 over N behavior here. Here, let me actually rewrite this. It's a little messy. So this is the N equal 1, just 1 over V rather. P goes as 1 over V. And then you have a little bit steeper one, which is N equal to gamma. Okay? And then in a TS diagram, the way this looks is the following, where you have TS, we'll do the N equal 1 case here. If PV is a constant, that if you look at the ideal gas law, then that means that you're going to be, the temperature will also be constant. And then you have this vertical line. This represents N equal to gamma. Okay, and that kind of should give you a pretty big hint that the N equal to gamma case is actually the isentropic case. So N equals 0 is that line, and then the steeper line here, like that, the N equal infinity, that is your, you can see is actually the V equals constant line. So what is this? What do I mean by this? N equals 0. This is your dP equals 0, right? Your iso bar, okay? N equals 1 is your T is constant, or dt equals 0, okay? N equals gamma corresponds to ds equals 0, and N equals infinity corresponds to your volume being constant. Let's try it this way, dV equals 0. Okay, so that's our polytropic processes. And that concludes our brief review of thermodynamics. I know it was a little, perhaps a little bit dense. Please feel free to reach out with questions. But regardless, in the next lecture, we'll actually start to bring in that other wing that makes up the compressible flow dyad between fluid mechanics and thermodynamics. We'll start talking about some fluid mechanics, control volume analysis, all that good stuff that will prepare us to go dive headfirst into this this topic. And before you know it, we'll be analyzing rocket engines and nozzles and shocks and supersonic flight and all of that. So yeah, see you next time.